In this video, I'm going to show you the solution to Exam 1 for Robotic Systems 1. I'm going to try and cover the most commonly made mistakes in each of these problems. Question number 1 shows you a picture of a manipulator, and it tells you to draw a kinematic diagram of this manipulator, but to only include the 3 joints labeled with arrows, and you don't have to label the diagram with frames, joint variables, or link lengths. So the first thing you want to do is identify what kinds of joints you have. Here we have 3 revolute joints. Next, you want to identify the direction of the axes of rotation. The first joint has its axis of rotation vertical. Then the axis of rotation of the next joint is perpendicular to the axis of rotation of the first joint, and the third joint has an axis of rotation that's parallel to the second joint but perpendicular to the first joint. So I'm going to draw that here. We'll do a cylinder. That's how we represent a rotational joint, a revolute joint. And this revolute joint has an axis of rotation that's up and down. So next, I'll draw a link and then another joint that's also revolute, and its axis of rotation is perpendicular to the axis of rotation of the first joint. Many people here drew their joint kind of looking like this, going up and down. I know it's hard to learn how to draw in 3 dimensions, and I can give you some pointers here. When we're drawing in 3 dimensions, you can only draw lines that are going in a couple of specific directions. Anytime you want to show something going up or down, the line will be vertical. If you want to show something going right or left, the line should be horizontal. If you want to show something going away from you or into the page, the line should be at a 45-degree angle in the first quadrant like this. And if you want it to be coming out towards you, you want to draw a line that's a 45-degree angle in the third quadrant. So that's why I drew this joint here with the lines defining the joint at a 45-degree angle between quadrants 1 and 3. So then I'll draw the third joint also at a 45-degree angle. So now we have the axis of rotation of the first joint being vertical, the axis of rotation of the second joint being into and out of the page, the third joint also into and out of the page. You'll notice that I didn't draw these joints necessarily in the same position that they're in the picture, and that's okay. Our kinematic diagram always shows how the manipulator looks when all the joints are set to their 0 angle. There's no particular reason to suppose that this picture is also showing the manipulator the way it is when all of its joints are 0. So as long as I have the relationship between the axes of rotation correct, and as long as I have links showing any place there's an actual link in the picture, then my kinematic diagram will be right for the picture. Question number 2 asks if this is a standard manipulator type, and if so, what type. Here you just have to look at lots of diagrams of standard types until you can recognize them. There is only one of our standard types that has 3 revolute joints, and that standard type really is defined as this picture shows, with the first joint having its axis of rotation vertical, and then the 2 additional joints have their axis of rotation perpendicular to the first but parallel to each other, and that type of manipulator is the articulated manipulator. Question 3 shows you a kinematic diagram that is unlabeled, and the question asks you to draw frames according to the Denevitt-Hartenberg rules and to label the joint variables and link lengths. So first of all, you know that we need to have 4 frames on this manipulator because we need to have 1 frame for each joint, and we also need to have a frame on the end effector. So we're going to go through our 4 Dennevit-Hartenberg rules. The first rule is that the z-axis has to be in the direction of motion for a prismatic joint or the axis of rotation for a revolute joint. So z of the first joint has to be either to the right or to the left. And I'm going to choose to the right, but that's just a personal choice. You could have made it go to the left. Z for the second joint has to be either up or down. I'm going to choose up. Z for the third joint has to be up or down. And then Z for the end effector can be any direction, but I'd like to try and copy the frame before it if I can. So for now, I'm going to put Z3 in the same direction as Z2. I might change that later on if I need to. All right, we're done with rule number 1. Rule number 2 is that the x-axis has to be perpendicular both to its own z-axis and the z-axis before it. So for frame 0, I could make z go into the page, out of the page, up or down. All of those directions would be perpendicular to z0, and there is no frame before z0, so that part of the rule doesn't apply. I'm going to make x go into the page. Keep in mind that just as I explained in question number 1 about the different directions and what they mean, when I'm drawing these frames, I can only choose to make my axes go up, down, right, left, into the page, or out of the page. I shouldn't be drawing any axes that are in this direction or in this direction. It's a convention that this one means into the page and this one means out of the page. These 2 other directions don't actually mean anything. Okay, now in frame 1, I can make x either be into the page or out of the page. Those are the only 2 directions that would be perpendicular both to z1 and to z0. I'm going to choose to make x0 into the page, or x1. For frame 2, I can either make x go right or left, or I can make x go into the page or out of the page, because all of those directions would be perpendicular to both z1 and z2. I'm going to make x2 go into the page for reasons that will become evident in a moment. And then I'll copy x2 in frame 3. Okay, now I have to think about rule 3. Rule 3 is that the x-axis has to intersect the z-axis of the frame before it. So that rule doesn't apply to frame 0 because there is no frame before frame 0. But the rule does apply to frame number 1. Right now, x1 will not intersect z0. So there are 2 ways I can solve that problem. One way is to try and change the direction of x1. That's the preferred method of solving the problem. However, in this particular case, I can't change the direction of x1. The only way that I could change the direction of x1 to get it to intersect z0 would be to make x1 be going up or down. And I can't do that because z1 must be going up or down, and then x would have to be in the same direction, and I can't do that. So I have to use the second method of solving the problem, which is to move the 1 frame. Now, it's important that you move the 1 frame as little as possible. And generally, the way that you achieve moving frame 1 as little as possible in order to get the x-axis to intersect the previous z frame is by moving the frame in the z direction. So in this case, the z direction is up and down. I'm going to move the center of the 1 frame only in this direction, and I'm going to move it down to right here. So after I move it, Z1 will be there and X1 will be there. This is the smallest amount I can move the 1 frame in order to get it so that it follows the rule where X1 has to intersect Z0. So that's where I'm going to move the 1 frame. Now you might think it's strange that the 1 frame is now not attached to any part of my robot, but in fact that actually doesn't matter. And one way to understand this is that we can imagine that there's a link, let's say, connecting between here and there, and that this axis is attached to the end of this link, and we would achieve the same thing. So the fact that there is no link here, as I've drawn in blue, doesn't actually matter. We've attached it to a sort of imaginary link there. So my 1 frame is no longer located here. It's now located down here. All right, now the reason why I previously drew x2 in this direction is to show you how we might solve this x direction problem the first way, by changing the direction. X2 does not right now intersect with Z1. It will bypass Z1. So the first way I should try to solve the problem is by changing the direction of X2. And in this case, I can solve the problem by making X2 go right or left. If X2 was this direction, it would in fact intersect with Z1. So I'm also going to change the direction of the X3 axis here also, because if I can keep frame 3 the same as frame 2, that will decrease the amount of math that I have to do in the future. So the last rule that I have to take into account is the right hand rule. I'm going to take my right hand and lay it out flat with my thumb sticking out as much as I can. And my thumb is going to become the z-axis. My fingers are going to point in the direction of the x-axis and the direction that my palm is pointing, or another way to think about it is the direction my hand is pushing, will be the y-axis. So for frame 0, y has to be up. Then for frame 1, y has to be going to the left. Then for frame 2, y has to be coming out of the page. And same for frame 3. We are now finished drawing our frames, and we're now going to draw in the joint variables. For prismatic joints, I just have to show that the positive direction of the joint variable is in the same direction as z. I'll call this D1. Then, for the rotational joint, the positive direction is determined by the right hand rule. I put the thumb of my right hand in the direction of Z1, and the direction that my fingers curl around shows the positive direction of rotation. I'm going to call this joint variable theta 2, even though it's just my first theta variable. The reason I'm doing that is because I'm showing that when this joint moves, when it turns, the frame that rotates as a result is frame 2, not frame 1. So when this joint, this revolute joint, turns around, frame 1 will stay just as it is. It's frame 2 that will rotate. So that's why I called this theta 2. Then my last joint variable, I'll call that D3 for the same reason. When this prismatic joint extends, frame 3 is the frame that will be affected. Lastly, I need to label the link lengths. The only thing that's important when labeling the link lengths is that every link length that shows up in my diagram gets a number. So I'll just start numbering them at any number. I'll start at 1. Let's call this one A2. Now I could label this link length A3 and then label this length A4. Or I could lump these two together into one link length. Same with A1 and A2. I could have lumped those two together into one link length. The rule that tells you whether or not you can lump together different lengths into one length is to ask yourself whether those two link lengths will always be in the same direction, no matter what the joints are doing. So, for example, let's call this link length here A5. A2 and A5 are in the same direction right now, but when joint 2 starts to turn, A2 and A5 will be in different directions. Because of that, I cannot lump together A2 and A5 into the same A variable. Okay, so I still have a link length here, which I'll call A6, and then we're done with this problem. There are a couple of ways that students on this problem tried to follow the rules of assigning the frames and accidentally did some things that are forbidden. One of those things is some people tried to move the 0 frame in order to get the x-axes to intersect. You can't move the 0 frame from where it is. The reason why is because the 0 frame represents the ground or the table or whatever it is that your first joint is fixed to. In your kit, this represents your board. Your board is already labeled with in centimeters, starting at the 0, 0 point on the ground, and that represents, say, a factory floor where we want to be measuring the position of the end effector relative to a particular point on the factory floor. So we don't want to move the 0 frame. That represents the thing that is immovable, the ground or the floor. Also, you can't move the frame that is on the end effector. The reason why is because if you don't have a frame that's actually located on the end effector, we'll have to go through an additional step later on to figure out where the end effector is. If you leave the frame on the end effector, then we can tell where the end effector is just by looking at our homogeneous transformation matrix. So you want to not move either the base frame or the frame that's on the end effector. All right, moving on to question number 4. Question number 4 says, shown here is a labeled kinematic diagram. There are at least 5 errors in this diagram. Find 5 errors and write in words what is wrong. So there may be more than 5 errors, but we only need to find 5. We're going to start out by thinking about the rules that we just used to draw the frames. We want to see if we can find any cases where the Z rule is broken, or the 2x rules, or the right-hand rule. Okay, so let's use orange to circle these maybe. For the Z rule, it's okay with the first joint, okay with the second joint, but with the third joint we have Z2, which is not in the direction of motion. So this is an error. Z needs to be the direction of motion. Okay, let's think about the other two rules. X has to be perpendicular to its own z-axis and the z-axis before it. X0 is okay, X1 is okay, X2 is okay, but X3 is not perpendicular to Z2, so that is an error. I'm going to circle this and say X3 needs to be perpendicular to Z2. So we've got 2 errors, we need to find 3 more. Let's think about the next rule. The next rule is that the x-axis has to intersect the z-axis before it. So that rule doesn't apply to the 0 frame because there is no frame before it. Does x1 intersect z0? It does not, so that's an error. I'm going to circle this and say x1 needs to intersect Z0. Okay, we've got 3 errors so far. X2 intersects Z1, but X3 does not intersect Z2, so that's another error. X3 needs to intersect Z2. The last rule is the right-hand rule. So I'm going to check each of these frames to see if it follows the right-hand rule. And the only one that does not is this 0 frame. The 0 frame violates the right-hand rule. Sometimes I abbreviate that RHR. Violates the right-hand rule. All the other frames are okay with the right-hand rule. The next thing I'll check is the direction of the joint variables. The 2 D variables are shown as being positive in the direction of motion, so they're okay. However, if I use the right-hand rule to find out what direction theta 1 should be, I find out that it's actually in the wrong direction. So theta 1 violates the right-hand rule. I've already found 6 errors. There's another error in here. If we check the link lengths, we'll see that one of the link lengths is not labeled. So right here in this distance here, this needs to be labeled link length, not labeled. And I think that's all the errors you could find in this diagram. Question number 5 shows us a labeled kinematic diagram and asks us to find the complete homogeneous transformation matrix from the base frame to the end effector frame by first finding the rotation matrices and the displacement vectors and then assembling into the homogeneous transformation matrix. So we know that each one of, let's start like this. The homogeneous transformation matrix from 0 to 3 can be gotten by multiplying together H01 times H12 times H23. So I need to find each of those individual matrices, and then we can get the final matrix by multiplying them together. Each of the individual matrices is made up of the rotation matrix, the displacement vector, and then 3 zeros and a 1 at the end. So in order to get each of these 3 homogeneous transformation matrix, I need to find R01, R12, and R23, and then I also need to find D01, D12, and D23. Let's start with the rotation matrices. Now, in my diagram here, you'll notice that the 2 frame is right on top of the 1 frame. That's because I had to move the 2 frame back in order to follow the Dennevit-Hartenberg rules. However, the behavior of the 2 frame is the same as it would be if it was stuck to the center of the 3rd joint. In other words, as the 2nd joint rotates, frame 2 will also rotate, although frame 1 will not. Okay, let's find R01 here first. The rotation matrix always needs to have 2 parts. One part for the joint variable, and then another part that tells how the 2 frames are rotated relative to each other right now in the diagram. The first part for the joint variable, we only need that part if it's a revolute joint, and frame or joint 1 is a revolute joint. So I'm going to go back up to the top here and get the standard rotation around Z. Since the joint is rotating around its own Z axis. So I'll do cosine theta 1, because that's the joint variable for the first joint, sine theta 1, 0, negative sine theta 1, cosine theta 1, 0, 0, 0, 1. Next, I need the part of the matrix that is telling me how frame 1 is rotated relative to frame 0 right now. X1 is in the same direction as X0. So remember that the columns represent X of the frame X, Y, and Z of the frame I'm going to, and the rows represent X, Y, and Z of the frame I'm coming from, that is frame 0. So since X1 and X0 are in the same direction, I get a column like that. Y1 is in the same direction as Z0. So Y1 and Z0 are in the same direction. And then Z1 is in the opposite direction as Y0. I'm going to erase these for now, just to give me some more space. And I'm going to multiply these 2 matrices together. There, I'm done with R01. Let's do R12. Joint number 2 is also a revolute joint, so I need this first part of the matrix. The only difference is that I'll put theta 2 in there. Now, I'm going to look at how frame 2 is rotated relative to frame 1 right now. X2 is in the same direction as Y1. Y2 is in the same direction as Z1. And Z2 is in the same direction as X1. I multiply these matrices together. And I'm done with that matrix. Let's do R23. Now, it looks as though there is a rotational joint between frames 2 and 3, but that's actually not the case. Frame 2 is the frame that came from the prismatic joint. I just had to move it into a different location in order to follow the Dennevit-Hartenberg rules. So there actually is no rotational joint between frame 2 and frame 3. So the only part of the rotation matrix I need is the part that tells me how frame 3 is rotated relative to frame 2 right now. X3 is in the same direction as X2. Y3 is in the same direction as Y2. and Z3 is in the same direction as Z2. You'll notice that what we came up with here is the identity matrix, and that's good because we know that the identity matrix means no rotation. Let's do the displacement vectors. D01 is the displacement from the center of frame 0 to the center of frame 1, like that. Now we want to write this vector in such a way that it will be true no matter how the joint variable theta 1 moves. Now, if you can picture in your head what this manipulator will look like as the variables are moving, you can see that this displacement vector, which I've drawn in purple, will actually stay the same no matter how theta 1 moves and no matter how theta 2 moves. So the displacement from 0 to 1 is only A1 in the z direction. Now let's do D12. D12 is very tricky because when you write it, it looks like it's wrong even though it actually is correct. Frame 2 is on top of frame 1 directly. No matter how theta 2 turns, the center of frame 2 is not going to move anywhere. So the displacement from the center of frame 1 to the center of frame 2 is 0 in x, 0 in y, and 0 in z. This will remain true no matter what happens to the joints. So the only vector we still need to get here is D23. Finding D23 is possibly the most difficult part of this problem. The reason is because it looks as though the distance from the center of frame 2 to the center of frame 3 will only be in the Z2 direction right now, and that as theta 2 turns, the center of frame 3 is going to move in the x2 z2 plane. But that actually is not true. As theta 2 turns, the frame 2 is also going to rotate along with it. Remember that frame 2 is the frame that was originally located right on the center of this joint. In other words, z2, x2, and y2 were originally in this location. You can see here that as theta 2 rotates, the center of frame 2 is going to move around in the x1, y1 plane. But the displacement from the center of frame 2 to the center of frame 3 is still going to be in the z2 direction no matter what happens with theta 2. That is still true, even though we've moved the center of frame 2 back to be on top of joint number 2. So the displacement from frame 2 to frame 3 is 0 in the x2 direction, 0 in the y2 direction, and in the z2 direction it's a2 plus a3 plus d3. And that is the D23 vector. Once you have the rotation matrices and the displacement vectors, all you have to do is recognize that you assemble those matrices and vectors in this way. In fact, if you stopped at this point with this problem, I would give you full points because you've shown how each of the parts have to be plugged into the respective matrices and then multiplied together. So we're done with this problem. I'm going to do question 6 right away also for the graduate students. The graduate students were asked to create a Denovet-Hartenberg parameter table for question 5. Since question 5 has 3 joints, our Denovet-Hartenberg parameter table needs to have 3 rows. Then I'll make a column for each of the parameters: theta, alpha, r, and d. Theta is the rotation around the z-axis. And the z-axis that we're looking at is the zn-1 axis. So for the first row, we're trying to see, how do I have to rotate frame 0 around the axis z0 in order to get the two x-axes to match, and also in order to account for the joint variable? Well, x1 and x0 already match, so I don't need any additional rotation beyond the joint variable in order to get those two axes to match. So theta in the first row is just theta 1. Let's do theta for the second row. We're going to ask ourselves, how do I have to rotate frame 1, shown in red here, around the z1 axis in order to get x1 to match x2 and also to account for the joint variable? x1 is pointing to the right and x2 is pointing up, so I would have to rotate frame 1 90 degrees around z1 in order to get x1 to match x2. I also have theta 2 as the joint variable rotating around z1. So here, theta for the second row is theta 2 plus 90. For finding the third row theta, we want to ask, how do I have to rotate frame 2 around z2 in order to get x2 to match x3? x2 and x3 are already in the same position, so I don't need any rotation to get those two axes to match. Also, there is no joint variable that is rotational between frames 2 and 3. The only joint between frame 2 and frame 3 is the prismatic joint. So the rotation theta for the third row is 0. Let's do alpha. Alpha is the rotation needed to get the two z-axes to match. And the axis we're going to be rotating around is xn. So I ask, how do we have to rotate frame 0 around the axis x1 in order to get z0 to match z1? z0 is pointing up and z1 is coming out of the page. So I need to rotate frame 0 90 degrees in order to get z0 to match z1. I also have to think about whether this rotation is positive or negative. So I put my thumb in the direction of x1, and the direction that my fingers curl is telling me the positive direction of rotation. So the direction that I have to move z0 is from up to out of the page. That's a positive rotation around the axis x1. So alpha for the first row is 90 degrees. For the second row, I have to ask myself, how do we rotate frame 1 around x2 in order to get z1 to match z2? z1 is coming out of the page and z2 is going to the right. So I have to rotate 90 degrees around x2. x2 is pointing up, so I put my right hand thumb pointing up, and the direction that my fingers curl tell me the positive direction. So the rotation from out of the page to the right is a 90-degree positive rotation. Lastly, to get alpha for the third row, I ask, how do we have to rotate frame 2 around the axis x3 in order to get z2 to match z3? z2 and z3 already match each other, so no rotation is needed. Let's do r and d. R is the displacement from the center of the frame, we'll do the first row first. So the center of the 0 frame to the center of frame 1, only measured in the xn direction, which here is x1. The center of frame 0 and the center of frame 1 are perfectly lined up in the x1 direction. The only displacement between these two frames is in the zn-1 direction, and that is d. So I'm going to put 0 for r and a1 for d. Let's do the second row. The center of frame 1 and the center of frame 2 are exactly lined up. That means that there is no displacement between the centers of these frames in any direction. I can fill in 0 for both r and d here. Now, the last row is about the displacement from the center of frame 2 to the center of frame 3. This displacement is entirely in the z2 direction. So I have a d value, but I have no r value at all. The displacement between frame 2 and frame 3 in the z2 direction is a2 plus a3 plus d3. When I'm done, I want to kind of double check myself by making sure that any of the link lengths that show up in my kinematic diagram also show up in my table, and that any joint variables that are shown in my kinematic diagram also show up in my table. And I see here that that's true. So my first check of this being correct looks okay. I didn't ask you to do the next step, which is find the homogeneous transformation matrix. If you wanted to find the homogeneous transformation matrix from the Stenivett-Hartenberg table, you would use this matrix right here and plug in the 4 values theta, alpha, r, and d for each row one at a time. So this would give you 3 different H matrices. It would give you H01 from the first row, H12 from the second row, and H23 from the third row. And you could then get H03 in the same way we did in the last problem by multiplying those 3 matrices together like this. But I didn't ask you to do that in this problem. Let's move on to question number 7. Question number 7 says, shown here is a kinematic diagram along with its homogeneous transformation matrix. There is a spray paint can attached to the end effector as shown in the diagram. When the link lengths and joint variables are set as shown, where is the spray paint can located and in what direction is it pointing? Answer by drawing the spray paint can on the provided 0 frame. The first thing I want to do is figure out where the spray paint can is located. I can do that by using the homogeneous transformation matrix. We know that this part of the matrix is the displacement vector. It's telling us where the center of the 3 frame is located relative to the 0 frame. So I'm going to take the numbers given here and plug them into these 3 values. The first value tells me my x position, the second value the y position, and the third value the z position. So the x position is equal to a4, which is 2, times the cosine of theta 3. Theta 3 is negative 90. So the cosine of theta 3 is going to be 0. So I'll stop here and not finish this first term because it's going to end up being 0. A3 is 1 and theta 2 is 90. The sine of 90 is 1. So I get 1 times 1. The x position is 1. Now the y position is a4, which is 2, times the sine of theta 3, 2, times the sine of theta 3. Theta 3 is negative 90. The sine of negative 90 is negative 1. And then plus a2, which is 2. So I get negative 2 plus 2, which is 0. And then we'll do the z position. The z position is a4, which is 2, times the cosine of theta 2. Theta 2 is 90. So the cosine of 90 is 0. This whole term is going to go away. I'll look at the next term. a3 is 1 times the cosine of theta 2, and theta 2 is 90. The cosine of 90 is 0. So that term is going to go away also. And all I have left is a1 plus d1. a1 is 1, d1 is 1, so the z position is 2. Now, I want to find the position 1, 2 on this graph here. So here's how I do that. I'll find 2 for z, and then I'm going to draw a diagonal line that's parallel to x0. Now I'll find 1 on the x-axis, and I'll draw a line that's parallel to z0. The place where these two intersect is the position x1, z2, and it's the position that is in the plane x0, y0. This has no y component. That's how we find a point in three-dimensional space. Let's suppose that we did have a y component. Suppose you were trying to find the position, for example, 1, 2, let me leave that there, and let's say you had 3 as the y position. What I would now do is draw a dashed line that is parallel to y0. Then I would also draw a dashed line that goes from the center of the frame out to this point. Then I'd find 3 on the y-axis, and I would dash a line from this 3 point that is parallel to this line that I just drew here. And the place where this line intersects this vertical line would be the position 1, 2, 3. That's how you draw and find a point in three-dimensional space. But in this particular problem, I tried to make it easier to draw by making it come out as a point that is in the x0, z0 plane. So this point right here is the center of the spray paint can. The only thing we need to find yet is what direction this spray paint can is spraying. In the kinematic diagram, the spray paint is spraying in the direction x3. So to figure out what direction it's spraying now, after we've set all of these values, we have to figure out what direction x3 is pointing. And we know that x3 is represented by the first column in the H03 matrix. So here I want to figure out what these 3 values are. I'll just draw a vector here. The sine of theta 2 is 1. And the cosine of theta 3, which is negative 90, is 0. So this ends up being 1 times 0, which is 0. Then the sine of theta 3 is negative 1, because theta 3 is negative 90. So the sine of negative 90 is negative 1. And then we do the cosine of theta 2, which is going to be 0. So this is our x3 position. And remember, this represents x0, this represents y0, and this represents z0. So the spray paint is spraying in the opposite of the y0 direction. So I'm going to draw a little spray here going down, like that. Now, I could also figure out what direction the can is pointing in. The can is lined up along Y3. So if I would take the Y3 column and find these numbers, I could know what direction the can is going. Let's see if we can do that here. The sine of theta 2 is 90. So the sine of theta 2 is 1. So I got -1 times the sine of theta 3. And theta 3 is -90. So the sine of theta 3 is -1. That equals +1. Since we've found a 1 in this column, we know that the other values in the column are going to have to be 0. So this is telling us that the Y3 direction is the same as the X0 direction. The Y3 direction is that way. So I could draw the can. In there like that. But for this problem, all I need to know is what direction the spray paint is spraying, and that direction is -Z0. So we've got the position and the direction of spray. We're done with this problem. Question number 8 says, here is a kinematic diagram of a 2 degree of freedom manipulator. Find the inverse kinematics equations. The first thing we need to do here is remember what inverse kinematics is, or what the goal of it is. The goal of the inverse kinematics equations is to take as input the position of the end effector in the base frame and output the values of the joint variables. So I need to end up with one equation that says d1 equals something something something, and theta 2 equals something something something. The right-hand side of this equation can only have things that are known. The things that are known are the link lengths and the position of the end effector in the base frame. The way that we get these two equations is by looking at the manipulator in either the top view or the side view, or sometimes both views. So I want to first decide which view I want to use to look at this manipulator. If I look at this manipulator from the side view, I'll be able to see D1, but I won't be able to see theta 2. However, if I look from the top view, I'll be able to see both D1 and theta 2. So I'm going to start out with the top view. It's possible I'll be able to get equations for both variables from that one view. When I look down at this manipulator from the top view, I'm going to see the Z0 axis pointing off to the right like this, and I'll see the X0 axis pointing up to the top. The first joint will just look like a square like that, and then there will be a link length, and then here's the second joint. Now, I want to draw theta 2 not in its 0 position. I want to draw it in a position like 45 degrees because I know that I need to find some triangles in order to solve for these equations. So the link A3 will look like this. It should be straight. There we go. Once I have this picture, I need to start to draw in the things that I know. And the things that I know, or the things that I can use as input, are the position of the end effector in the base frame and the link lengths. This distance right here is the position of the end effector in the base frame. Now, in this case, I have frame 0, there's a frame 1 not shown on this second joint, and then frame 2 is on the end effector. So I can call the position of the end effector in Z, Z02. And this distance here is the X position of the end effector in the base frame. Those are the two things I want to use as my input. Now, some people tried to draw a frame 1 and then label the position of the end effector in frame 1. You don't want to do that in inverse kinematics because we don't know where the end effector is in the 1 frame. We only know where it is in the base frame because we're specifying the location where we want the end effector to be relative to the ground or relative to the floor. We don't necessarily know where we want it to be relative to one of the joints in the linkage. So you can't draw in an intermediate frame and then use those variables in your inverse kinematics. The other thing I want to label is link lengths. This is A3. And then this distance here is not just A1, but it's actually A1 plus D1. A1 plus D1, and D1 is one of my joint variables. I need to make sure to label the joint variables in this picture because that's what we're trying to solve for. This is theta 2. So now I have my joint variables, the position of my end effector, and the link lengths. I should have everything I need to find some equations. Now, oftentimes we want to draw some triangles to help us find these equations. There is one triangle here that is likely to be useful to us. It's this triangle right there. The reason why this is likely to be useful to us is because some of the sides are known. We know A3 and we know x02. And one of the angles, theta 2, is a variable that we're looking for, that we're trying to solve for. So right away we can write one of the equations that we need. We can use SOHCAHTOA to know that the sine of theta 2 is the opposite over the hypotenuse. The opposite side is the x position of the end effector, and the hypotenuse is A3. So we could solve for theta 2 right away here. And that's one of our equations. We still need another equation for D1. I'm going to box this and call this equation 1. How could we solve for D1? Well, A1 is a known quantity, and Z02 is also known. That's one of our inputs. So let's give a name to this distance right here. I'm going to call that R. Then I can write an equation that says that D1 is equal to Z02 minus A1 minus R. I'm not quite done yet because I haven't said what R is equal to. But I could find R from either theta 2 or by using the Pythagorean Theorem. For example, I could say that the tangent of theta 2 is x02 over R. And then I could solve for R. I could call this equation equation 2, and then I could call this equation 3. I can do that because by the time I get to equation 2, we've already solved for theta 2, so we can solve for R. And once we've solved for R, we can solve equation 3 for D1. There are more ways that are correct to do this than this one. For example, we could have used the cosine of theta 2 to get R. Or I could have used the Pythagorean Theorem to get R from A3 and x02. There isn't just one unique solution to inverse kinematics. There's often more than one way to do it. But since I ended up with two equations that solve for my two joint variables, I'm done with this problem and we'll move on. Okay, question 8 is only for the graduate students, and this is also a inverse kinematics. If we look at this manipulator from the side view, I'll be able to see D2, but I won't very well be able to get theta 1 or D3. If we look from the top view, I'll be able to see theta 1 and d3, but I won't be able to see d2. So almost certainly I'll have to use both the top view and the side view for this manipulator. I'm going to start with the top view because I think that is a little bit easier to start with. In the top view, we'll see x0 pointing off to the right and y0 pointing up to the top. The first joint will look like a circle right there. The second joint and the third joint will both be right on top of it. But I'm not going to draw this in such a way that theta 1 is 0. I'm going to draw it where theta 1 is 45 degrees. So joint number 2 and joint number 3 will both look kind of like that, squares. And then there is the link A3. Now, what I want to label here is all of the joint variables that I can see, the position of the end effector in the 0 frame, and any link lengths. So here we have the y position of the end effector in the base frame. The end effector frame in this case is going to end up being 3. So I'm going to call this y03. And here this is going to be x03, the x position of the end effector. Then for joint variables, here I have theta 1. And then this link length right here is going to be A3 plus D3, and D3 is a joint variable. So let's see what equations I can get. An equation for theta 1 I think is the easiest here. Theta 1 will be the arctangent of y over x. And then we can get D3 also from this using the Pythagorean Theorem. So I'll do A3 plus D3 squared is equal to x03 squared plus y03 squared. And I want to solve for D3, so I'll start by square rooting both sides, and then I'm going to subtract A3 from both sides. So we end up with D3 is equal to the square root of x03, that's a 3, squared, plus y03 squared, and then minus A3, and that minus A3 is not inside the square root. So here I already have an equation for theta 1 and an equation for D3. I still need an equation for D2, and in order to get that, we're going to have to use the side view. So let's do the side view. In the side view, I'm going to look at this manipulator in such a way that my view is perpendicular to this link. I'm looking from out of the page perpendicular to that link. And keep in mind that theta 1 might be rotated to any angle. So in my side view, the only axis I can rely on here is Z0. X0 and Y0 might be pointed in any direction depending upon what the angle of theta 1 is. So from the side view, here's my first joint, and then I've got the second joint, the third joint, like that, and Z0 is pointing up. But going to the right may or may not be x0, so I'm not even going to draw that in. Now I want to label anything I know about the position of the end effector. This is the position of the end effector in the z direction. Next, I want to label any link lengths and joint variables that I have. This here is A1. This here is A2 plus d2. And right now, I don't know what this is. We can find it out if we need to figure that out, but since I don't know yet whether I even need that, I'll leave it unlabeled for now. I think I can find an equation for d2 just with the things that I have now. So z03 is equal to a1 plus a2 plus d2. So all I have to do now is solve for d2. And here we have our third equation. We have one equation for each of the joint variables, and the right-hand side of each of these equations only has things we know. The position of the end effector in x, y, and z, the link lengths, and nothing else. That's all that's in the right. Okay, on to question 9. Question 9 says, here is a rotation matrix. Is this a valid rotation matrix? Why do you think so? How can you tell? Most people correctly recognize that this is not a valid rotation matrix, but many people misunderstood the reason why we can tell that this is not a valid rotation matrix. Many people said that the reason it's not valid is because there are two numbers in one column, and we cannot have two numbers in one column. But that's not true. We often can have two numbers in one column. In fact, we could have three numbers in one column. One way we can tell this is that our standard rotation matrices, instead of writing it here, I'm just going to scroll back up to the top. In our standard rotation matrices, many of these columns have more than one number in them. Suppose that theta is 45 degrees, for example. Here, in the first column of the RZ matrix, cosine of 45 is non-zero, and sine of 45 is also non-zero. So we would end up with two numbers in the same column. The reason we know this is not a valid rotation matrix is not because there is more than one number in a column. Probably the easiest way to tell that this is not a valid rotation matrix is to recognize that if we would take each of these numbers, there's 0.8, square it, and add up the other numbers in the same column or row, this does not equal 1. Remember that each column of a rotation matrix is telling us the projection of an axis on the x, y, and z axes of another frame. In any kind of a frame that we have, let's just do x, y, and z. In all of these frames, we always assume that the length of each of these axes is 1. So the length of x is 1, the length of y is 1, and the length of z is 1. So when we project these axes onto other axes, we can figure out, let me show an example here. Let's suppose that I had another frame, let's call these 1. Let's suppose I have another frame where the z-axis is in the same direction, but the x2 is that way and the y2 is this way. If we would project x1 onto these two axes and take these distances, these are the distances that would show up as the numbers in this rotation matrix. If we wanted to figure out what was the length of this arrow here, x1, I'll call these things A and B, we could find out the length of that vector by taking A, squaring it, B, squaring it, and square rooting it. That's the Pythagorean Theorem. That will tell us the length of x1. Since in all of our frames we assume that all of the axes have a length of 1, it better be that when we square the projection on one axis, square the projection on the next axis, add them up and square root them, we end up with the length of the axis. This is also true in 3 dimensions. So if x1 was rotated in such a way that it had a projection on the x2 axis, the y2 axis, and the z2 axis, we know that if we would square up each of those projections on x, on y, and on z, and then square root them, we would have to end up with the length of x1. And the length of x1 is always the length of 1. So the easiest way to tell that this is not a valid rotation matrix is that the length of the axis turns out to not be 1. Another way you could have said that this rotation matrix is not valid would be to say that one of these two numbers has to be the sine and the other has to be the cosine of an angle. And there is no angle theta that would give you 0.8 as the sine and 0.8 as the cosine also when the length of the vector is 1. So you could have said there is no angle that makes this true. Or another thing you could have said is that these projections, if all these numbers are correct as projections, what you have as the frame that is being projected is not an actual frame because x, y, and z are not perpendicular to each other if this is the projection that you get on a valid frame. So there's a number of different ways you could have explained the rotation matrix is not valid. You got some points for recognizing that no, it's not valid, and then you got some points for giving a valid reason how you know that this is not a valid matrix.